Chapter 4 takes what you just saw and says, is there something similar to this that happens for any vector space at all? And so what we're going to look for is transformations or a mapping that meets the following things. And we're going to have some mappings that have some special properties, and we're going to call these particular mappings linear transforms. The idea behind this is the following. So over here, I have vector space V. Over here, I have vector space W. What are vector spaces? Right? Anything that meets those 10 axioms. Right? We define what addition means. We define what scalar multiplication is. The vector spaces that we all know are the normal nth dimensional spaces, continuous functional space, polynomial of a fixed number of term space, matrix space, right? Things that have all those little properties. And what we're going to consider is some sort of mapping that would take things in one. We'll say this is x1 and say x2. So I have vectors, whatever they are. So if this space was continuous functions, then each of those things, instead of being like an arrow, it's a function. Right? It's a continuous function like sine or cosine. And then I'm going to map them to some other vector space. So I could map continuous functions to three-dimensional space. I could map the polynomial vector space to a continuous functional vector space. So we're just taking these things and just mapping across and seeing, okay, what's going on as I do this. But if I do, one is going to go somewhere. So let's say that this guy here is, this thing has taken x1 and moved it there. And let's say this thing has taken x2 and moved it there. That's what a mapping does. Just simply moves stuff. Whatever type of vector this is and whatever vector space it is. I'm moving it from one to the other. Then I'm going to restrict myself to not simply say, okay, there's a lot of ways that we could do this, right? How many ways can you have a relationship? How many ways can you have a function, right? But we're going to restrict the types to certain properties. And what we're going to restrict this to is finally saying for the following definition. This mapping L that is going to take things from V into things to objects in W is going to be called a linear transform if the following holds. You would take alpha x1 plus beta x2. So that says, look on the left-hand side, and what do? I take a linear combination of these two vectors, which is really, when you do something like that, that's all you're saying is, take this vector and stretch it, take this vector and stretch it, and then add them together. It's kind of like the parallelogram rule with some stretchings, right? That's what we do. So I look on the left-hand side and say, hey, take these two and just do a normal linear combination. So you do a nice normal linear combination on the left. And then, after you do that, map the result. So on the left-hand side, you would take, okay, I'm going to do my parallelogram rule. I'm going to figure out what the result would be. And then I'm going to map the result. Something like that, right? So I'm going to restrict myself to the transforms that are going to be special in such that when you map the result, it would be the same thing as if you had taken, where did x1 go? Where did x2 go? And then it has the exact same transformation. In other words, this little blue arrow isn't going to be here. It's going to say, oh, that transformation is going to be, this linear combination right there. So you'd say any linear combination on the left will still be the exact same linear combination, the same stretchings, the same alpha, the same beta, as the mapped stuff on the right. One way of considering this is it doesn't cause any sort of like warpings. It's like, oh look, well how do I get, if I have this vector and this vector, just do a linear combination, you get that vector. And then, well, how would I figure out where that went? Well, I would take one way of looking at this is take your basis vectors. Where do they go? What was your linear combination on this side? It's the linear combination on the other side of the exact same form. In other words, it essentially maps this in a nice way. So anything that does this, when you look at it, it says a linear combination of your domain is the same linear combination of your images. Linear combinations are preserved in a way, kind of considering that. All right, what are things that do this? If you didn't want to, one of the things you can do because eventually you're going to have to show this equality. It's like, hey, here's a linear transform. It's like, well, you just called it a linear transform. That means you need to show that any linear combination of a pre-image is equal to the same linear combination of the images. You have to show this equality to be true. Well, you have this x1, x2, alpha, beta. It's pretty complicated. So if you don't want to do it with one large thing that has these 4 variables, because, well, what is x1, x2? Anything. What's alpha, beta? Anything. We have 4 anythings that I have to worry about. If you don't like that, you could turn this into a 2-step rule. And the first step would be show that addition works all by itself, and then show that scalar multiplication works. And if both of these work, they actually would work in conjunction. What's nice about the 2-step is instead of having 4 unknowns at the same time, I'm only dealing with 2. It's like, well, what's x1, x2? It's anything. Well, how do I represent anything? You'd have to go through here. It's like, hey, what is anything within 3-dimensional space? A, B, C. Where I don't know what A, B, C, and are. So what if I need 2 of those? A, B, C, D, E, F. And now I have to do all my work. You have to have, like, what are all the possible ways of working with this problem? And you have to kind of go through it. So, example. Let's say that I'm going to have a transform, let's call it T, that's going to take let's do a kind of a classic example. Any continuous function over AB and spit out a real number. So on this side, I have CAB. What does CAB look like? It's any function that's continuous over AB. And what's obviously R1? Well, it's pretty easy to represent. It's a real number line. All right, how am I going to map a continuous function to a number? Well, the way I'm going to do this is I'm going to let T simply work on a function by calculating the area under the curve. So that's my transform. That's how I'm going to map. How much is its net signed area? right? If it's all below the curve, it's a negative number. If it's above the curve, it's a positive number. So this is the net signed area thing. Every function is just going to, from between A and B, every continuous function can be obviously mapped to what's its area. And that's what happens. So I'm going to take functions and map them to their area. Is it a linear transform? So is that rule, so T of F simply equal to the area under F over AB. It's actually net signed area, which means that I allow negative areas, even though area normally has no definition in terms of negative. Like if I gave you a circle and somebody says, oh, you have -1 square units. It's like, that's retarded. I mean, areas are positive. It's like, well, not for this. Net signed area allows for such things as being negative because you interpret anything above as being a positive amount, anything below being a negative amount. All right, so if that thing is happening, is it a linear transform? So what do I want to check? Is it true that, let's say we do our two-step version. 1, that if I would take vector 1 and vector 2, is that the same thing as vector 1 transformed, vector 2 transformed? Is that true? All right, well, first off, what's a vector? What space am I in? Continuous functions. So what's my object? It's a continuous function. So what do I want to study? This L of x1, x2 is really, if you integrate from A to B, of f1 plus f2 dx. Right? Well, what's one of the properties of integrals? It splits, right? And so this is actually equal to the integral from A to B of f1 dx plus the integral from A to B of f2 dx. By the way, what is that? So this was L of f1 plus f2. And what's this? Well, that's just the area under f1, and that's the area under f2. Is it true? Yeah. The area under the sum of functions is the sum of the areas. We already knew this, and that's all. That's what you would check. That'd be 1. The second thing to worry about is, well, what if I want to take an alpha x1? It better be alpha L of x1. Well, is that true? Well, what is L of alpha f1? That is equal to what? I integrate from A to B of alpha f1 dx. That's how I do the transform. Where is this alpha allowed to be? It can slip out the integral. And so this is alpha, the integral from A to B of f1 dx, which is equal to alpha L of f1. So, yep. So this is true. And that's true. So mapping a continuous function to its area is a linear transform. In other words, linear combinations of the functions is linear combinations of the areas. If you take a function, multiply it, take another function, multiply it, and add it together, that's the same thing as taking the area and multiplying it by the same number, and taking the other area, multiplying it by the same number, and adding them together. It's a nice transform, so it's a linear transform. And so that's how you would check on each of those. Now, some other ones that, since we don't always just stick with things like continuous functions, let's say that we would take, for example, let's say L is going to map from three-dimensional space to two-dimensional space. And the way it does this is L of a three-dimensional object, say x1, x2, x3 is going to spit out a two-dimensional object, which is, say, x3 and then x1 plus x2. So I'm taking three-dimensional space, and there's this transform that spits out two-dimensional space. So here's three-dimensional space. Here's two-dimensional space. So for example, where would L of, let's say this vector right here is, say x positive 1, y is 2, and z is 1. Say that's, this vector is right there. Where would it get mapped to? What do I put in the top spot? 1. What do I put in the second spot? x1, x2, right? So what's happening? In the first spot, you put that one. In the bottom spot, you add those two and put that one. And so where's this going to get mapped to? 1, 3, which is this guy right there. So that three-dimensional vector gets mapped to that two-dimensional vector. Is everybody okay with that? So this is just moving stuff. Well, how does it move it? Your first coordinate is your third coordinate, and your second coordinate is take your first two coordinates and add them, and that's your second coordinate. That's how you go up or down. Why? Don't care. It's just the rule. Now the question is it a linear transform? So that's an example of how it runs. Well, to check if something is a linear transform, there's two ways that you check this, right? You could either check both the stretching and addition in one step, or you could do it in two steps. Which one do you want to do? You want to do a two-step check or a one-step check? One-step check? Okay. So we're going to check, is it true that if I would take alpha 1, x1 plus alpha 2, x2, and transform it, is that the same thing as taking L of x1, L of x2, transform those x's, and then go ahead and doing your linear combination? Okay. x1 and x2 are coming from what space? Right, that's where the x's are from. So what is this? This is any x1. How many coordinates does that have? 3. So I'm going to have to replace it, so we need to check this. I don't know if this is equal, so let's try. This would be L of alpha 1, which is, I don't know, ABC, plus alpha 2, CDE. Is everybody okay with that? I could have used x1, x2, x3, or q1, q1. It's just, I have 3 coordinates, right?
Do they need to be different?
They have to be different because they're different vectors.
So we can't use C twice?
Nope, because they'd be different C's. Where did I do? That's really good on my part. my you see, D, E, F. Thank you. Everybody okay with that? And then what do I need to check? I need to check, is this the same thing as alpha 1 of L of ABC plus alpha 2 L of DEF? I need to see if those are equal. Now, I haven't yet done the transforms, but what does the transform say? I know how to do the transforms. Well, first off, those transforms I can do right now. What does the transform work on? The transform works on a single vector. It takes the bottom, puts it first, and it takes the top two and adds them and puts it second. That's how this transform works. Here's my issue. Is this a single vector? Not yet, but if I go ahead and add them. Sure. And so this would be, I need to transform A alpha 1 plus D alpha 2, B alpha 1 plus E alpha 2, C alpha 1 plus F alpha 2. That is now a single vector. And I need to check if this is equal to alpha 1. Well, let's go ahead and do that transform. Okay, what's the rule of the transform? It is take the bottom, write it, take the first two, add them. So if you transform A, B, C, what would you get?
C, A plus B. F equals D, or equals C.
Is everybody okay with that? All right. Transform that. What would you get?
C, F2.
Is everybody okay with that? Are these equal? Just break across alpha 1, alpha 2. Right? What are the things with alpha 1? What are the things with alpha 2? So if I go ahead and break them across like that, this is alpha 1, and there's C alpha 1s on the first, and there's A plus B alpha 1s on the second, and an alpha 2. Well, there's an F alpha 2 up here, and there's a D plus E alpha 2 on the bottom, and the answer is yes. So this is a linear transform. Seems kind of odd that it was like, so yeah, it's like a linear combinations of these three-dimensional vectors would still be the linear combination of the two-dimensional vectors after the transform has occurred. They preserve linear combinations, so it's a linear transform. If you would show that it would be impossible to be equal, you would say, no, it's not a linear transform. So all these problems of yes or no is you do this work and you look at it and say, is it possible for these to be equal? If they are equal, like as you look, it's like, yes, they're equal. It's a linear transform. If you show that they cannot ever be equal, then it would be no, it's not a linear transform. Like, for example, if I did the thing on the right and your answer was that the top was supposed to be like that was a 1, right? And then you would get to this point and you would say, well, wait a second, that's a C and that's a 1. Those can't be equal unless C's 1, but C could be anything. So, no, they are not the same thing. And so, not being a linear transform. And so some of the homework problems are, some are, and some are not. And they all get down to, this would be, can you start to see where if you have a lot of unknowns, it kind of gets a little bit, the algebra gets a little bit complicated because there's a lot of stuff going on. It's one of the reasons why when you break it up into two, the complexity's there, but it's in 2 steps. Let's do one, it's not as bad. And let's do the other one, it's not as bad. So. All right, what are some properties of linear transforms? If the vector space you're starting from goes to the vector space, which is the same thing, and so if you go from, say, R2 to R2, continuous functions, to continuous functions, polynomials to polynomials, instead of calling it a linear transform, since it only has the codomain and the domain of the same vector space, you use the word linear operator on that vector space. And so it's a special name. we would just go ahead and call L a linear operator on V. One of the ways of considering this is just this concept of, instead of having this look, V to W, this is the idea of, kind of the idea of a transform. The idea of an operator versus a transform is to sit there and say that instead of saying that I'm going from V to V, is to take this V and just pull it back into the other one. And imagine, instead of having your domain and your codomain being completely different locations, would be to consider that I would take this entire space and just say that the transform looks something like this. So L goes from V to V, and so we call that one a linear operator. In other words, it's kind of staying within the same space. The idea of a transform versus an operator is just this idea of, instead of going to a new space, it's actually still working in the same space. So I could imagine vectors in this room, and I do something to the vectors in this room, but instead of going to the room beside us, we say that it stays within this room. So like a rotation, that'd be a linear transform. So if I have around the origin, and I would take every vector in this room and just simply rotate it around in a particular way around the origin, that would be a linear transformation. And it's, on the other hand, since it stays within the same space, we just rename it and say it's a linear operator. It's an operator within the vector space. We're not going somewhere new. And so it's kind of just a psychological approach to saying that, instead of like room A going to room B of completely different dimensions and completely different objects, it's room A back to room A. The second thing is a linear transform of the zero object in your V space is going to always go to the zero object of your other space. Zero objects go to zero objects, always on a linear transform. So origins get mapped to origins. 3. The definition of a linear transform only had two vectors that you added and stretched. It was a linear combination of two. But that would mean that since a linear combination of 3 is really a linear combination of 2, right? So if I would say things like, well, what if I had alpha 1, x1 plus alpha 2, x2 plus alpha 3, x3? Well, that is actually a single vector, right? By the commutativity and associative property, linear transforms still work. And so a linear transformation of 3 would be the same thing as linear combination still works on post-transform. So that would mean that my definition can be considered that it doesn't just simply go to 2, it can go to however many you want. To prove linear transformation, you need 2. But by associativity and commutativity, you can go as high as you want. So then that should start to look familiar. That would be any linear combination at all of a set of vectors, which is a span. But what's the right-hand side? A span of the transform. In other words, what's going to happen here is, so if I take a element of a span, it's going to have to go to the same linear combination for the transformed basis itself. And so you can take entire spans, and they are preserved by linear combinations. The fourth is, what does that symbology mean? If I put a minus vector, what am I really saying? It's a vector's what? Additive inverse. It's the part that gets you back to the origin. And so it says, like, well, what would happen if I would transform the additive inverse of a particular vector? It would go to the additive inverse of the transform vector. In other words, additive inverse is mapped to the same additive inverse. Other things of interest would be, we already saw something that did this with like the null space, like I did at the beginning of class, right? The null space was every vector that mapped to the 0 object of the codomain. And then I could say, well, again, we still have our V, we have our L, we have our W. Over here I have the 0 object of W, whatever it is. It's continuous functional space, it's just the function equals 0. If it's polynomial space, it's 0 plus 0x plus 0x squared plus, well, how many terms did you need? If it's polynomial 5, you need 5 terms. And so you go through it, and that's my 0 object. And so one of the things I could ask for, hey, what are all things over here that go there? It's exactly the same mindset of what the null space does. The null space is what are the nth dimensional objects that map to the 0 dimensional object of Rm. And now we're going to say, well, what does this work? What about any arbitrary vector space? Well, we won't use the word null, even though it's going to be like the null, because we've moved up to say not just simply Rm and Rn, like normal space. We're going to do, what about functions? All right, that'd be the same thing. Let's go back to our problem for a second that I did for this transform. So if this transform is find the area under the curve, what continuous functions between A and B would go to a net signed area of 0? Any idea? Because that's what I'm kind of interested in. I'm saying, hey, which of these objects go to the 0 object? Well, the 0 object of R1 is 0. So here's a straightforward one. How about this? That has area 0. But on the other hand, what about this? That would have area 0. So what are the things that map to 0? They have the same amount above as they do below. I'm not going to be able to write them down, but I can definitely describe it. It's the continuous functions where they have the same amount above the x-axis as they do below the x-axis, so that when I add them together, the net signed area will be 0. On the other hand, what if I said it's the continuous functions, but I restrict myself to the ones that are only positive? They never go below the x-axis. It would only be this. That would be the only guy who would ever go to 0. It would be the 0 function maps to 0. And that's that one definition. The 0 always goes to 0. Well, that's a 0 function. It definitely goes to 0. But who else does? So those are the sorts of questions that you could have. It's kind of like the null space is. And we give it a completely different name, though. So instead of asking things like, okay, who all is going to go to the 0 space, and so 5, we're going to define what's called the kernel, which is ker. And I'm just going to collect every vector possible in V such that when I map it, it's going to go to the 0 object of the W space. It's kind of like the null space. But now we're not talking about just normal nth dimensional space. We're allowing things like polynomial space and continuous functional space and vector space. What's a 0 object? Got to think about it. What are all things that are going to do this? And that would be called the kernel. And the sixth one that may be interested on this is the idea of, if I have a subspace on the left, where does he go? What's an image? I can take a single function and find its area. I can take a single vector and find a vector. But what if I take a bunch of them, take a subspace and move the entire thing? And that would be So if S is a subspace on that left-hand side, the image of S is going to be written as L of S. Just map that entire subspace. L of S is going to be equal to what's everything on the right-hand side, such that there exists a vector in the subspace such that L of V is to W, is equal to W. And B, L of V is range of L. So the entire range is to take all of V and move it. And if I take all of the vector space and move it, it's going to be the range of that transform. If I just take part of that space and move it, that'd be at least the image of that subspace. For both of these, the kernel and the subspace, the image of S, everybody who goes to the zero object and the image of a subspace are both going to be subspaces. The kernel is a subspace of V, and L of S, where it goes, is going to be a subspace of W. So the range of an entire vector space is a subspace of one on the right-hand side. Everybody that gets mapped to the zero object is also a subspace. It shouldn't be that big of a surprise because the null space was shown to be a subspace. And the column space you can show to be a subspace, which is what this is acting as in a similar concept. So let's try another example. Let's say I'm going to take D, which is going to map P2 to P2. Where, first off, what is P2? These are term-term polynomials, which would look something like what? Like A plus BX. So these are all linear polynomials, right? Except now what I'm going to do is say that D is the derivative. That's just, so this is a mapping. What's it going to do? A polynomial comes in, I take its derivative, that's what comes out. So for example, what is the derivative of 2 plus the square root of 3x? Square root 3. What is D of 4? 0. And actually, if I would write square root of 3, what does square root of 3 look like as a P2 object?
0x.
And what's 0 look like?
0x.
If I would write it as P2, I have to write both terms. Right. P2 means 2 terms. You got to write 2 terms. So this is obviously taking things that are a polynomial of 2 terms and spitting out a polynomial of 2 terms. Right? Now, here's my question. So we kind of understand what's happening, right? It's taking a polynomial. Well, first off, is it a linear operator? What's a linear operator? Right? Show that All right, else D. All right, alpha 1 obviously was alpha 1. But what's x1? Where's it from? What's it? This is a thing. What is this? This is what? This is in P2. What is this? In P2. What's an arbitrary thing in P2? Something plus something x. So, I don't know, a plus bx. Plus alpha 2. So, c plus dx. Is this going to be equal to alpha 1 times the transform of a plus bx plus alpha 2 times the transform of c plus dx? Is everybody okay with that? It's just something in P2. Well, what is it? I don't know. Something x. Something to put things there. What are a and b and c and d? Any constant. What's alpha and alpha 2? Alpha 1, alpha 2? Any constant. Now, on the other hand, take the derivative of that. I could multiply and combine, blah, 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 blah. Take the derivative of that. What are you going to get? That's what this D says. Take the derivative. If I would take this and distribute through, take the derivative of the first, what are you going to get? 0. Why? Because it's a constant, right? Should I multiply it out and have it? Are we all okay with this? What's going to be the derivative of this? Alpha 1b. And so this would be alpha 1b plus alpha 2d plus, how many x's do you see? 0x. It's a little important. You always have to write it in two terms. What are the constants? Alpha 1b plus alpha 2d. All right, does this equal alpha 1? What's the derivative of that? B. Plus alpha 2 times? D. Plus? 0x. Are they the same? Yes, they're equal. It's a linear transform. So the derivative is actually a linear transform. So that would say that the linear combinations of two polynomials is going to be the linear combination of the derivatives of those two polynomials. So you take the derivative of a linear combination, it's the same thing as taking a linear combination of the derivatives. Okay, so that's fine. It is a linear transform. So we can always check that. What else could we check on this? What do you think the kernel is? What is the kernel asking?
What goes to 0?
I want what goes to 0. The question is, the kernel of a thing is give me everything in your vector space such that d of that thing goes to 0 object of the other vector space. Well, that is what? 0 plus 0x. And so what we're asking for is the derivative of what always spits out 0 plus 0x.
B has to be equal 0.
B has to be equal 0. So when I look at this, when I try to solve that, that's equal to, that's B, right? Plus 0x. And so what are my restrictions on A? And so that ends up being that, so what are these vectors? The kernel of D looks like what? Some sort of A plus 0x. Another way of writing that would be P1. If I want to write it, because P1 is just the constants, if I want to write it that way. Or you write A plus 0x, your choice. Is everybody okay with that? And so those are the things that you kind of go through and you ask, all right, is it a linear transform or not? Can I find the kernel? Can we find images? And study all those. Now, the hard part about a lot of this is, linear transforms, like, so for example, where's that one? That weird one, like this, right? This was a linear transform. it takes a three-dimensional object and spits out a two-dimensional object. Well, how does it work? I take the third coordinate, write it first, take the first two coordinates, add them, and write them second. It's a process. Now, this process is a transformation. I'm manipulating it in a particular way. Now, one of the things that we had before is it sure looks like, multiplication by A may be a linear transform. And so A is m by n, and I kept drawing it this way. Hey, I multiply by A, it takes this Rn, it spits out an Rm, and kind of the question is Ax a linear transform? And let's call it, say, L of A, which is mapping Rn to Rm. So it's moving stuff. It is a transform. But is it going to be a linear transform? So how do we check those things? I need to take the linear transform and take alpha 1, x1 plus alpha 2, x2, and check if this is alpha 1, the linear transform of x1 plus alpha 2, the transform of x2. Are these equal? Well, first off, how do you do the transform? You just multiply by x. That's what we were doing. It's like, what is my transform? I multiply by this matrix A. Didn't I multiply by x? I multiply by A. So I'm taking A and multiplying by alpha 1, x1 plus alpha 2, x2. Well, is this going to be equal to alpha 1 times A, x1 plus alpha 2, A, x2? Because that's how the transform happens. It just simply says multiply by A. Well, what is one of the properties of matrix multiplication? Is there a left-hand distribution? Yes. Can a scalar go in front of a matrix vector? In other words, what do I have? I have a matrix multiplying alpha 1 x1 plus a matrix multiplying alpha 2 x2. What's one of the properties of matrix multiplication? If you stretch one of them, you could actually have stretched last, pull it out. And so that's actually equal to alpha 1 ax1 plus alpha 2 ax2. Those are just simply properties of matrix multiplication. Are these equal? Yes, they're equal. So matrix multiplication is a linear transform. Well, that's kind of nice. So yeah, it's a linear transform. But actually what's really nice is the following theorem. You have a linear transform that was given like we did at the very beginning of the class. Take the third coordinate, write it first, take the first two coordinates and add them and write them second, which is this process that we have to do over and over again. Given any linear transform, there exists a matrix A such that the linear transform is the same thing as the matrix multiply. So what I showed just now was a matrix multiplication is a linear transform. What this theorem says is actually any linear transform that you can think of at all, going from n-dimensional space to m-dimensional space, there will be a m by n matrix that does the exact same thing. And not only that, if you want to find A, which is obviously A's first column, A's second column, A's to the nth column. To do this, you just have to take the standard basis and transform it, the standard basis, transform it, and then the nth standard basis and transform it. And you can quickly find it by just simply transforming your standard bases. And that will become the columns of A. So that would mean that when we had this guy, L of x1, x2, x3, spitting out a two-dimensional object, x3, x1 plus x2, well, we would have, what's A? We would just take L of 1, 0, 0. We would take L of 0, 1, 0. And we would take L of 0, 0, 1. Where will 1, 0, 0 go? 0, 1. Where will 0, 1, 0 go? 0, 1. Where will 0, 0, 1 go? All right, there you go. Multiply by that, it'll do exactly, what does this matrix do? It'll take the third coordinate, write it first, and then take the first two coordinates, add them, write them second. It'll do the exact same thing. And we'll study more of this as well as scale up to in terms of transformations next time.